Hi, I'm Mark Barsamian with the Ohio University Math Department. In section 4.1, we began discussing plane separation. We started discussing plane separation in drawings. The idea that in a drawing, a drawn line kind of splits the plane of the drawing into two half planes. And points of the plane are either on the line or in one of those half planes or the other. And we discussed the way that drawn segments either intersected that line or did not intersect that line, depending on whether the endpoints of the segment were on the same side of that line or on opposite sides of that line. And then we discussed the idea that in our axiomatic geometries, there's so far been no mention of this kind of behavior. There's nothing in the axioms for abstract geometry or incidence geometry or metric geometry that articulates anything about that kind of behavior having to happen. So we discussed what's called the plane separation axiom, which is basically a description in the terminology of our axiomatic geometries, a description of that kind of desirable plane separation behavior. And again, there's nothing in our geometries so far that specifies that kind of behavior has to happen. So there's nothing in our geometries so far that specifies that the statements of that plane separation axiom would have to be true for a given geometry. Then in section 4.2, we discussed that for our most familiar metric geometries, the Euclidean plane, the taxicab plane, and the Poincare plane, actually the plane separation axiom is satisfied. So those metric geometries that we're most familiar with already have that desirable plane separation behavior. Well, then that leads us to kind of an obvious question. If our most familiar metric geometries already have that kind of desirable plane separation behavior, do we need to have an axiom that requires that kind of behavior, or could we maybe just have a theorem that says actually in metric geometries this kind of behavior is always guaranteed? Well, that's the subject of section 4.3. In 4.3, we'll start with that question. Do all metric geometries actually have that desirable plane separation behavior? And we'll see that they don't. We'll find an example of a metric geometry that doesn't have that desirable plane separation behavior. It doesn't satisfy the plane separation axiom. So if we want to confine our work from now on to geometries that do have that kind of desirable plane separation behavior, that is the geometries that do satisfy that plane separation axiom, then we should define a new class of geometries. That is those ones that do satisfy that plane separation axiom. And so that's what we'll do in this section 4.3. This material is produced for Ohio University Math 3110-5110 College Geometry. The material for this video is from section 4.3, Pash Geometries, in the book Geometry, a Metric Approach with Models by Millman and Parker. As I mentioned before, the topics will be, we'll start with this question, is the plane separation axiom always true for a metric geometry? And then we'll discuss what's called Pascha's postulate, and then what I'll refer to as two equivalent statements in a metric geometry. We'll discuss the missing strip plane. That'll be the example that I mentioned earlier of a metric geometry that does not satisfy the plane separation axiom. And then finally, we'll define Pasch geometry. And we'll end the video with a discussion of what's called Peano's axiom. The homework for this video is this short selection of 5 exercises from section 4.3. Now, let's recall some stuff from old sections that will be useful. From way back in chapter 2, section 2.1, there's this useful corollary. Given two lines in an incidence geometry, if those lines are known to be distinct, that is, they're not equal as sets, then either those lines don't intersect at all or they intersect in exactly one point. So that's corollary 2.1.7. And then recall the definition of a partition of a set and convex set from section 4.1. We'll be using those ideas a lot because they're used in the definition of the plane separation axiom from section 4.1. plane separation axiom says for every line, there are associated two sets of points called half-planes with the properties that these three sets, the line and those two half-planes, form a partition of the set of all points. And also, each of the half-planes is convex. And finally, if one point is in one of the half-planes and another point is in the other half-plane, then the segment that connects those points intersects that line that created those half-planes. And also recall from my discussion of section 4.1 in these videos that it's useful to know the contrapositives of plane separation axiom statements 2 and 3. So plane separation axiom 2 says that the half-planes are convex. Well, that can be articulated as a conditional statement. If two distinct points are in the same half-plane, then the segment that connects them does not intersect the line. And the contrapositive of that statement is if the segment that connects two distinct points does intersect the line, then the 2 points are not in the same half-plane. Plane separation axiom 3 is already stated as a conditional statement. If 2 points are not in the same half-plane, then the segment that connects them does intersect that line. The contrapositive of this is also true. If the segment that connects two distinct points does not intersect the line, then those two distinct points are in the same half-plane. From section 4.2, we discussed the plane separation axiom for the Euclidean and Poincare planes. We discussed the definition of half-planes for those geometries, and the idea that the Euclidean plane satisfies the plane separation axiom, the taxicab plane satisfies the plane separation axiom, and the Poincare plane satisfies the plane separation axiom. So here we are in section 4.3. Having seen that our three most familiar metric geometries, the Euclidean, taxicab, and Poincare planes, all satisfy the plane separation axiom, a reasonable question is this: is the plane separation axiom true for all metric geometries? The main object of section 4.3 is to answer that question. Now, in order to answer that question, we're going to first learn about what's called Pasch's postulate, and then we'll determine the relationship between the plane separation axiom and Pasch's postulate, and then finally we'll study an example of a metric geometry called the missing strip plane. Pasch's postulate is the following. We say that a metric geometry satisfies Pasch's postulate to mean this. For every line and for every triangle, if the line intersects a side of the triangle at a point that's not a vertex, then the line intersects at least one of the opposite sides. Now we can illustrate this with a drawing. So in the left diagram, we have a picture of the hypothesis. We have a triangle, we have a line that intersects one of the sides of that triangle at a point that is not a vertex. In the right drawing, we have a picture of the conclusion of that postulate. We show the line intersecting at least one of the opposite sides. Now, just for convenience, shown that particular side, the one on the left, but it could be either one or both. Now I want to talk about the relationship between the plane separation axiom and Pasch's postulate. There's a theorem that's not articulated in the book. I've formulated it here. I call it a theorem about two equivalent statements in a metric geometry. So given a metric geometry, the claim is that these two statements are equivalent. That is, they're either both true or both false. The first statement is the metric geometry satisfies the plane separation axiom. The second statement is the metric geometry satisfies Pasch's postulate. So either a metric geometry satisfies both of those things or it doesn't satisfy either one of them. It's the idea of this theorem. And again, this is not articulated as a single theorem in the book. A proof strategy for a theorem like this could be this. In proof part 1, prove that if 1 is true, then 2 is true. That is, if a metric geometry satisfies the plane separation axiom, then the metric geometry also satisfies Pasch's postulate. Well, this is the subject of the book's theorem 4.3.1, and that's proven in the book, but I'll also do a proof of that in the video. Part 2 of a proof of this theorem would be the following. Prove that if 2 is true, then 1 is true. So prove that if a metric geometry satisfies Pasch's postulate, then it also satisfies the plane separation axiom. Now this direction of the proof is very difficult. It's done in the book on pages 76 and 77 in theorems 4.3.2 and 4.3.3. I won't discuss those proofs in this video, but I do want to point out that this single idea that those two statements are equivalent, the plane separation axiom, Pasch's postulate, is embodied in the book's theorems 4.3.1, 4.3.2, and 4.3.3. So this theorem is just a sort of a rebranding of 3 existing theorems in the book. So here's proof part 1. Remember, proof part 1 is to prove that if 1 is true, then 2 is true. So statement 1 is the metric geometry satisfies the plane separation axiom. So the proof structure of the proof would be you start by saying, well, suppose that's true. Suppose that the geometry does satisfy the plane separation axiom. And for a direct proof, the proof should end by saying the metric geometry satisfies Pasch's postulate. So let's go look at the end of this proof. So therefore, the metric geometry also satisfies Pasch's postulate. That's the end of proof part 1. So there's the direct proof structure that we would expect. Now what else can we expect? What other proof structure is inevitable? Well, let's jump back down to the end and look at that final statement. Our goal is to prove that the metric geometry satisfies Pasch's postulate. Well, let's go back up and look at what Pasch's postulate says. Pasch's postulate says, for every line and for every triangle, if the line intersects the side of the triangle at a point that's not a vertex, then the line intersects at least one of the opposite sides. So to prove that Pasch's postulate is satisfied, you have to demonstrate that for any given line and triangle, if that green stuff is true, then that red conclusion is true. So a proof that Pasch's postulate is satisfied is going to have to start by saying, suppose all that green stuff is true, and then show that therefore all that red stuff is true. Well, let's go back down and look at our proof again. So we want to end by saying that Pasch's postulate is satisfied. So to get here, we're going to have to, at some point, said, well, suppose all that green stuff is true, and then prove that therefore all that red stuff is true. So let's go back up to the beginning. In statement 2, we have this suppose. Suppose that a line L intersects side AB of a triangle at a point that's not a vertex. That's the hypothesis of Pasch's axiom. And now let's go down towards the end of the proof. Statement 10 says that line L intersects at least one of the sides. So that statement there is the conclusion of Pasch's postulate. So that pair of statements, starting with statement 2, and then ending with statement 10, that pair of statements, 2 and 10, is a frame for a proof that Pasch's postulate is satisfied. So in statement 11, we're called upon to justify this statement, that Pasch's postulate is satisfied. Well, the justification for that is by statement 2, which said, suppose that the hypothesis of Pasch's postulate is satisfied, and statement 10, which says, then therefore the conclusion of Pasch's postulate is in fact satisfied. So the justification for this final statement of the proof is going to be by 2 and 10 and the definition of Pasch's postulate. So now we have this inevitable proof structure. The proof has to begin with statement 1. We have to have this frame consisting of starting with statement 2 and ending with this statement 10, comprising a frame of a proof that Pasch's postulate is satisfied, because we had to end with that. Now let's get to work filling in the inner part of this proof. So we have to illustrate statement 2. We don't have to prove it because we can't prove it. We're supposing that it is true. Well, we've already illustrated this statement before. This is this statement that's the hypothesis of Pasch's postulate. We drew that earlier when we were illustrating the statement of Pasch's postulate. So let's go up and grab that drawing and copy it and bring it back down here. There's the drawing that illustrates the hypothesis of Pasch's postulate. I'm going to copy that drawing and move it back down, and when we get down to back to the proof, we'll find that drawing there waiting for us. So there's the drawing that we had before. Let's add to this the points that are mentioned in this statement 2. Let's go on. Statement 3 is, associated to line L are two half-planes. We have to justify that and illustrate it. Well, the half-planes exist by the plane separation axiom. Since we're in a geometry that satisfies the plane separation axiom, we can use the fact that for every line there are two associated half-planes. So that's the justification for the statement. What's the illustration of the statement? Well, let's draw the line and draw its half-planes. I'm going to draw the line in black this time. So there is an illustration of the line L and its half-planes. Statement 4 says point A is in one of those half-planes. We have to justify this, and then we can give that half-plane a name, let it be called H subscript A, and then we have to illustrate that. Well, that's a fairly straightforward thing to illustrate. By plane separation axiom I, we know that this collection of sets, the line and the two half-planes, is a partition of the set of all points. And we know that A is not in line L because of statement 1, or statement 2, I guess that is. Line L intersects the triangle at a point D that's not a vertex. Well, A is a vertex, so the A must not be on that line. So to illustrate this, I can just simply copy that drawing from statement 3, bring it down, and add point A to it. So that's our illustration of statement 4. Statement 5 says point B is not in half-plane A. So we can let this symbol denote the half-plane that contains point B. Now we're supposed to justify this statement that B is not in half-plane A, and then we're supposed to illustrate this. Well, by statement, this should be statement 2. By statement 2, let's go up and look at that. Statement 2 says line L intersects side AB at a point that's not the vertex. By that statement and Psa2 contrapositive, let's go up and look at that. Psa2 contrapositive says if a segment does intersect the line, then the points are not in the same half-plane. So by statement 2 and Psa2 contrapositive, we know that A and B are not in the same half-plane. Now let's illustrate that. Let's go up and copy that drawing from statement 4 and bring it down. So I'm going to copy this drawing and bring it down, and we'll find it there. Now before scrolling down, let's add to this drawing this symbol that was mentioned that is the name of the half-plane that contains point A. So let's go back down. There's our drawing that I copied down here. I put B in the other half-plane, and we should add the names of these half-planes. So there's an illustration of statement 5. Statement 6 says there are three possibilities for point C. Either C is in half-plane A, or C is in half-plane B, or C is on line L. We have to justify that. Well, that's just simply because that set of three sets, the line and those three half-planes, is a partition of the set of all points. So I keep misspelling partition, and that set of three sets should be labeled differently. Okay, now we have articulated a big OR statement. One of those three things, at least one of those things, is true. We in fact know that's exactly one because that's what a partition is. Well, remember that in a proof, when you arrive at an OR statement that you know is true, you have set yourself up for a proof by cases. So the proof from here will become a proof by cases. Case 1 will be, suppose that C is in half plane A. Well, in that case, the claim is that segment BC intersects line L. We have to justify that and illustrate. Well, let's start with the illustration. Let's show a picture where C is in half plane A, and then show a picture where segment BC intersects line L. I'll make my drawing by copying this drawing from above and bringing it down. And I'm going to copy it again. So the hypothesis, C is in half plane A, is illustrated by just putting C in over here on the left. And the illustration of the conclusion, BC intersects line L, I'll put over here on the right. So there is an illustration of what this statement is saying. The justification for this statement is, well, it's by Psa2, and that should be Psa3. Psa3 says, because B and C are not in the same half plane, segment BC intersects that line. So there's the justification, and then this is the illustration. And the second case is statement 8. If C is in half plane B, then segment AC intersects line L. We have to justify that and illustrate that. Well, that's going to be the same sort of drawing and justification that we just did. So I'll start by making two copies of the drawing from above. I'll start by putting C in half plane B, and then I'll make a copy of this drawing and move it over. And then in the second drawing, I'm going to show segment AC intersecting line L. And the justification for this statement is, again, Psa3. Let's go on. Case 3 is in statement 9. If C is on line L, then both AB and BC intersect line L. We have to illustrate that. I'm going to bring the same drawing down again. So I'm going to copy this drawing here and bring it down, and when we scroll down, we'll find it. So there's our drawing. Now on the left, we should draw the hypothesis. The hypothesis is that C is on line L. So I will put point C right on line L. And the conclusion is that AC and BC both intersect line L. So I'll copy this drawing and move it over to the right. Now to illustrate this conclusion, I'll just draw those segments. And I don't really need to justify, it's clear that this is true because C is an element of both segments. And so we can now state the conclusion of those cases. We can say that line L intersects AC or BC or both. And the justification for that is, well, because it's true in every case. So now we've completed the proof, the sort of mini proof, starting with statement 2 and ending with statement 10, that proves that Pasch's postulate is satisfied. Well, that's the end of proof part 1. As I said, proof part 2 would be to prove that if 2 is true, then 1 is true. That's the harder direction of the proof. For that, see the book. Let's go on. Now I want to talk about the missing strip plane. Remember the question that was posed at the start of the video. Is the plane separation axiom true for all metric geometries? Well, the answer to that question will be found in a new geometry called the missing strip plane. We'll start by defining a peculiar set of points in R2. What I call strip is the set of all ordered pairs of real numbers such that x is greater than or equal to 0 and less than 1. So this set here. So on the left of that pink stripe is the solid vertical line with equation x equals 0, and that's included in that shaded set. And on the right boundary is a dotted line that has equation x equals 1. The fact that that vertical line x equals 1 is dotted indicates that that line is not part of this set. Now we're going to use that set called strip to define the missing strip plane. First of all, the set of points in the missing strip plane is the set of all ordered pairs of real numbers minus the ones that are in that strip. So in other words, it's going to be the set of all ordered pairs of real numbers such that x is less than 0 or greater than or equal to 1. So this set of numbers. Now in this diagram, the dotted line is the line with equation x equals 0, and that's not part of the green set. The solid line is the set with x equals 1. That is part of the green set. So that green set is the set of points in the missing strip plane. Now the lines in the missing strip plane consist of sets that are a Cartesian line L minus the points that are in that strip. So here are some examples of lines in the missing strip plane. So for point A equals 2, 5, B equals -1, -1, and C equals 2, -1. Line CA is maybe the easiest one to think about first. This is an ordinary line, an ordinary Cartesian line. When I subtract the red points from that blue line, it's unaffected. So this blue line, this blue set here, is a set of points that qualifies as an ordinary Cartesian line, and it also qualifies as a line in the missing strip plane. Now think about line BC, missing strip line BC. Well, that's going to consist of ordinary Cartesian line BC minus these points. So what's left is these two pieces. On the left piece, there's an empty dot. On the right piece, there is a solid dot. That's because, remember, this vertical dotted line indicates that points with x equals 0 are not part of the missing strip plane. So this blue set that has a chunk missing in the middle is a missing strip line. Similarly, missing strip line AB is this set. It's ordinary Cartesian line AB minus this chunk in the middle. So those are examples of lines in the missing strip plane. Let's go on. Now in homework exercise 4.3.4, you'll prove that the missing strip plane is qualified to be called an incidence geometry. Note that in order to do this, you'll need to first prove that that missing strip plane is qualified to be called an abstract geometry. In the book on page 79, the authors mention that you'll be proving that the missing strip plane is an instance geometry, and then they go on to prove that the missing strip plane is actually a metric geometry. Their proof of this fact is very interesting. It uses a theorem that we did not discuss in our course, theorem 2.2.8. That's an interesting theorem. I don't want to get too bogged down with the missing strip plane, so we won't discuss that proof. But since the missing strip plane is a metric geometry, it will have segments and triangles. Remember, segments are something that you could only define when you had the notion of betweenness, which meant that you had to have a metric geometry. So here's an example of segments and a triangle in the missing strip plane. So those same 3 points, A, B, and C, that gave rise to those lines in the previous example. This example, we showed lines AB, BC, and CA. Those 3 points give rise now to segments. Segment AC, segment AB, and segment BC. Notice that segment AC looks just like a segment in the Euclidean plane. But segment AB and segment BC have these missing chunks. And then triangle ABC, well, that's going to be the union of those 3 line segments. Triangle ABC is shown there. It's got a missing chunk. Now for example 3, I want to point out that the missing strip plane does not satisfy Pascha's postulate. So let's pull up our same triangle. Here's point A, here's point B, here's point C. Let's let point D be over here at -2, 2, and let point E be over here at 3, 2. Let's put some coordinates on our other points. Now let's put some points on the locations where the Cartesian-looking lines are interrupted by that missing strip. So there is that missing strip triangle with that new missing strip line, DE, drawn in. Now here there's some typos. Okay, so notice that line DE, this black missing strip line, intersects side AC of that triangle at this point F here, that has the property that F is between A and C. So the hypotheses of Pasch's postulate are satisfied. We have a line that intersects one side of a triangle at a point that's not an endpoint. But that line does not intersect either of the other two sides of the triangle. Why? Well, because the place where you'd expect those lines to intersect, here, that location, is not the location of a point in the missing strip plane. So line DE does not intersect either of the other two sides of the triangle. So this shows that the missing strip plane does not satisfy Pasch's postulate. Now remember the theorem about two equivalent statements from 10 pages ago. It told us that the plane separation axiom and Pasch's postulate are equivalent statements in a metric geometry. That is, they're either both true or they're both false. Well, we have an example, the missing strip plane, in which Pasch's postulate is false. So that means that for the missing strip plane, the plane separation axiom is not satisfied either. So that finally provides the answer to our question from a while back. The question was, is the plane separation axiom true for all metric geometries? Now we can see that the answer is no. There are metric geometries that don't satisfy the plane separation axiom. So having seen that not all metric geometries satisfy the plane separation axiom, we realize that if we want to be sure that a geometry does satisfy the plane separation axiom, we need to make it a requirement. And so we're going to define a new class of geometry called a Pasch geometry, and that's going to be a metric geometry that satisfies the plane separation axiom. Now, remember, by that theorem about two equivalent statements in a metric geometry, we realize that Pasch geometries will also be the metric geometries that satisfy Pasch's postulate. So let's take a moment to discuss some of the types of geometries that we've studied before. We studied abstract geometries. We had examples like this, the Riemann sphere, examples like this. We discussed the Euclidean plane, taxicab plane, Poincare plane. All of those things were qualified to be abstract geometries. But when we added some additional requirements to define instance geometries, some of the geometries got knocked off. This abstract geometry is not an instance geometry. The Riemann sphere abstract geometry is also not an instance geometry. But all of these geometries were instance geometries. Then we added some more requirements to define metric geometry. Now, one of the requirements of metric geometry, remember, is that every line has to have a ruler, and that means every line has to have an infinite set of points on it. You realize that this geometry that is qualified to be called an instance geometry is not a metric geometry. And of course, any geometry that fails to be an instance geometry is also not going to qualify to be a metric geometry. A bunch of other examples that we did study, there are most familiar metric geometries, the Euclidean, taxicab, and Poincare plane, those are all metric geometries. The plane that we didn't study as much, the max plane, is a metric geometry. And then this new missing strip plane is a metric geometry. And finally, in the current video, we defined a new class of geometry, the so-called Pash geometries, and we realized that that missing strip plane that is qualified to be called a metric geometry is not qualified to be called a Pash geometry. So it's not included in the collection of Pash geometries. And of course, all of these other geometries that failed to be metric geometries also failed to be Pash geometries. But these remaining geometries, the Euclidean, taxicab, max, and Poincare planes, all of those are still in the running. That is, they're qualified to be called Pash geometries. Now I want to discuss what's called Peano's axiom. These words, to say that a metric geometry satisfies Peano's axiom, mean this. Given a triangle ABC and points D and E such that C is between B and D and E is between A and C, given all that stuff, there exists a point F on line DE such that F is between A and B and E is between D and F. So let's illustrate this. Let's put the given stuff in a diagram on the left. There's an illustration of all the given stuff. The point D that has the property that C is between B and D, and the point E with the property that E is between A and C. Now let's make another copy of this diagram over on the right. What Peano's axiom says is that there exists a point F on line DE, so let's draw that, that has the property that F is between A and B, so that's illustrated there, and also E is between D and F, so that's illustrated there. So Peano's axiom says this: if you have this configuration of points, then you also have this, the existence of this, the guaranteed existence of this additional point F. The question I want to raise now is Peano's axiom always true? Now, earlier in the video, we posed a question and eventually found an answer. The question was, is the plane separation true for all metric geometries? We found the answer was no. There is an example in the missing strip plane that illustrates that the missing strip plane did not satisfy Pasch's postulate. And so, therefore, the missing strip plane also does not satisfy the plane separation axiom. So an obvious question now is Peano's axiom true for all metric geometries? And the answer is going to be no. In one of your homework exercises, you'll be asked to provide an example in the missing strip plane metric geometry that illustrates that the missing strip plane does not satisfy Peano's axiom. Now, the following theorem tells us about one situation where we know that Peano's axiom will be satisfied. I call this theorem PSA arrow PA, or if the plane separation axiom is true, then Peano's axiom is true. So the claim is, given a metric geometry, if the metric geometry satisfies the plane separation axiom, then the metric geometry satisfies Peano's axiom. So let's illustrate and justify the statements in a proof of this. First of all, let's think about the proof structure. The claim is if a metric geometry satisfies the plane separation axiom, so that's going to be our statement 1. And then the claim says then the metric geometry satisfies Peano's axiom. So let's go down and look at the very end of this proof. The proof ends by saying the metric geometry satisfies Peano's axiom. So we've got the direct proof structure that we know to expect. Now let's think about what else to expect from this proof structure. Our goal is to prove that metric geometry satisfies Peano's axiom. But what does Peano's axiom say? Peano's axiom says if you have all this given stuff, that configuration of points, then there exists this additional point f with these certain betweenness relationships. So to prove that Peano's axiom is satisfied, we're going to need to prove that if all that stuff is true, all that green stuff, then that red stuff is true. So look, our proof, step 2 says, suppose all that green stuff is true. That's the hypotheses of Peano's axiom. Now let's go look down towards the end of the proof. Statement 15 is, we've proven that there exists this point f with these certain betweenness relationships. That's the conclusion of Peano's axiom. So this pair of statements, starting with statement 2 and then ending with statement 15, this pair of statements is a frame of a proof that Peano's axiom is satisfied. So that is what we'll use for justification for statement 16. So this should say by 2 and 15 and the definition of Peano's axiom. So statement 2 is where we say, suppose the hypothesis of Peano's axiom is satisfied. In statement 15 is where we said, therefore, the conclusion of Peano's axiom is satisfied. So that blue pair of statements, 2 and 15, have to be there in order to end by saying that Peano's axiom is satisfied. So having seen why the proof has to start and end the way it does, let's go back up and start filling in the justifications and illustrations in the proof. All right, so statement 2 says, suppose a triangle is given along with these points D and E that satisfy these betweenness relationships. We don't prove that, we just say suppose that's true. Now, to illustrate that, we can just go up and grab our previous illustration of the hypothesis of Peano's axiom. There's a drawing of the hypothesis of Peano's axiom. So I'm going to copy that drawing and move it down, and when we go back down, we'll find it there. So there's our drawing. Now, part 1 of the proof is we're going to show that there exists a point F on line DE that has this betweenness relationship. So to start with, statement 3 says, Pasch's postulate is always satisfied. We have to justify that. Well, that's because in statement 1, we said, suppose we've got a metric geometry that satisfies the plane separation axiom. Then we have this theorem that says if a metric geometry satisfies plane separation, then it also satisfies Pasch's postulate. So that's what allows us to say that our metric geometry satisfies Pasch's postulate. Statement 4 says line DE intersects segment BA or segment BC. We have to justify that and illustrate that. Well, the justification of that is going to be by statement 2. Now, statement 2 says that we have this configuration of points. And what else? Well, we're going to use Pasch's postulate. And here, this describes how we're going to use it. Well, let's go up and get that drawing from statement 2 and bring it down. So I'm going to copy this drawing and move it down. We'll have it down there when we go back down. So there's the drawing that we have in statement 2. And then Pasch's postulate, if we apply that to line DE, let's draw that line in here. That line intersects triangle ABC at point E that's not an endpoint. And so Pasch's postulate says that that line intersects at least one of the other two sides. Now, the instructions say to illustrate, but I'm not going to illustrate because we don't actually know which side this line is going to intersect. I mean, it sure looks like it's going to go on down and intersect side A, but that's just because of the way that I drew it. I could have drawn this some other way in which it might look like the line's going to intersect another side. So I'm just going to leave this drawing as it is. But in fact, that line DE cannot intersect side BC. Now let's go up and look at our drawing. Remember I said it looks like this line is going to go on down and intersect AB. It doesn't look like it can possibly go over here and intersect side BC. But we have to say in words why we know that's not going to happen, not just say, well, it doesn't look like it could happen. Well, in words, let's notice that lines DE and BC intersect at point D. Now that's illustrated in the drawing, but it's true because of the words that we've spoken already. These two lines, line DE and line DB, they both contain the point D. So there's no drawing necessary to say that those lines intersect at point D. Now, those lines are not allowed to have any other intersections by that corollary 2.1.7 that says if two lines are distinct lines and they intersect, they're only allowed to intersect in one point. And we know that point D is not in segment BC because of this betweenness relationship. C is between B and D. So these two lines, the green line and the blue line, only intersect at this one point, this point here. And that point is not part of this segment because of the betweenness relationship that says C is between B and D. So all of those statements are part of the justification of this, saying that that line can't intersect segment BC. Let's go on. Statement 6 says, therefore the line has to intersect segment BA. We have to justify that. Well, that's by 4 and 5. Statement 4 says that line has to intersect one or the other of those segments, or maybe both. But statement 5 says it can't intersect BC, so therefore it has to intersect BA. So there's our justification for it. Now, the instructions say to illustrate, but I'm going to cross that out. I don't want to illustrate yet because we don't actually know yet for sure where that point of intersection is going to have to be. So that's what the next couple of steps are about. Step 7 says the point of intersection can't be point B. Now, why is that? Well, that's the same kind of reasoning we had before. We already know that point B is not on line DE because DE and BC only intersect at point D. So this green line and this blue line only intersect at this one point. So the place where this green line is going to intersect segment AB cannot be at the endpoint B. Now, statement 8 says the point of intersection can't be point A. Well, the justification for that is going to be similar. We know that lines DE, that green line, and line AC, that blue line, we know that they intersect at point E. So that green line, DE, and that blue line, AC, are known to intersect at point E. They're not allowed to have any other points of intersection by that corollary that says two distinct lines can only intersect at one point. Now, so therefore, I see we've got a typo here. So therefore, the point of intersection cannot be point A either. So before we go on, we have proven that line DE has to intersect this segment, and we've proven that the point of intersection can't be the endpoint B, and it also cannot be the endpoint A. Well, statement 9 says, therefore, the point of intersection must be a new point called F that's between A and B. Well, that's because of what I just said. We know that that green line intersects segment AB by statement 6, and we know that by statements 7 and 8, the intersection is not one of the endpoints, so the only remaining option is a point F that's between A and B by definition of line segment. Line segment AB only consists of point A, point B, and points that are between A and B. So we've proven that DE intersects AB at a point F that has that betweenness relationship. That's part of what we needed to prove. The claim is that Peano's axiom is satisfied. Remember, what Peano's axiom says is if you have this configuration of points, then there exists this point F that has this betweenness relationship and this betweenness relationship. Well, so far we've proven that there is a point F that has that betweenness relationship. That's the end of the proof part that we were just working on. So we've proven that there's this point F that has that betweenness relationship, and that's the end of proof part 1. Now, finally, we're ready to illustrate. We know exactly where to put our point F. It's got to be between A and B. So we can go up and get our most recent drawing and modify it. So here's our most recent drawing, and I'll bring it down, and we'll find it there when we go back down. So there's our drawing. Now what we need to do now is add this point F. So let's get rid of the green line that we have and draw a new one and put in our point F. So that's the state of things so far. Now what we're trying to prove next is that that other betweenness relationship is true. We want to prove that E is between D and F. Now, of course, if you look at this drawing, it certainly looks like E is between D and F, but we need to prove that it's true based on the words that we've said so far. So here we go, part 2. We start with this statement that points F and B are in the same half plane of line AC. Now, why is that? Notice it sure looks like it. Here's line AC, and here points F and B over on one side. Well, in fact, let's make the drawing first and then see if we can justify. So here's line AC, and then let's draw one of its half planes. And then let's put F and B in that same half plane. So there's an illustration of this statement. Now we have to justify it. Well, remember, how can you ever justify saying that 2 points are in the same half plane? Let's go back up and look at the plane separation axiom. The plane separation axiom, statements 2 and 3 and their contrapositives are shown here. Now, of these 4 statements, the only one that ends by saying, therefore, 2 points are in the same half plane is this one, Psa2 Contrapositive. So the strategy will be this. We have to prove that the segment does not intersect the line, and then use Psa2 Contrapositive to say, therefore, those endpoints of the segment are in the same half plane. Here we see that this strategy is borne out. We're going to use Psa2 Contrapositive, and we have to start by proving that the line does not intersect the segment. Well, so how do we know that line AC does not intersect segment FB? Well, it's because this. Line AC and line AB can only intersect once at point A. And furthermore, A is not on segment FB because of this betweenness relationship. F is between A and B. So in this diagram, maybe we could make it clearer by showing the segment very clearly. So we know that line AC does not intersect segment FB, and so therefore F and B are in the same half plane. And that's what this diagram shows. Statement 11 says points B and D are in different half planes of line AC. Well, now let's think about how that's going to have to be justified. The only way that you can ever justify saying that 2 points are in different half planes is by using Psa2 Contrapositive. And the strategy is you have to first show that the line intersects the segment at a point that's between the endpoints of the segment, and then you can use Psa2 Contrapositive. Well, we do know from statement 2, way back at the very beginning of the proof, that line AC intersects segment BD at a point C that's between B and D. Let's go back up and look at that diagram at the very beginning of the proof. In statement 2, we assume this is the configuration. Now, what we're observing in particular currently is this. This green line, AC, and this blue segment intersect at point C. So that tells us that B and D are on opposite sides of that green line. And so then we can use Psa2 Contrapositive to say that B and D are in different half-planes. So let's add that to our drawing, or let's highlight that in our drawing. So there's a diagram that not only illustrates the fact that B and D are in different half-planes, but it also mentions this point C that was used in the explanation of why we know that B and D are in different half-planes. And so therefore, F and D are in different half-planes of line AC. Now why is that? In statement 10, we knew that F and B are in the same half-plane. In statement 11, we said that points B and D are in different half-planes, and so therefore F and D are in different half-planes. That's the justification by 10 and 11. Now how do we illustrate that? Well, we can just take our existing drawing and modify it a little bit. So there's an illustration of the statement that F and D are in different half-planes. Now I'm going to add to this the point B that's over in that same half-plane with F. So finally, statement 12 says, therefore, line AC intersects segment FD at a point that's between F and D. Now, how can we ever justify that kind of claim? We can only use PSA 3, that is, using the fact that F and D are in different half-planes. PSA 3 says, therefore, the line intersects that segment at a point that's between the endpoints. So let's illustrate this by copying the drawing from statement 12 and just adding that segment. So there's that point that's temporarily just called point, and we see that it is between F and D. Statement 14 says, well, notice that line AC is already known to intersect line DF at point E. And those two lines can only intersect at one point. That's by corollary 2.1.7. Two distinct lines cannot intersect in more than one point. So therefore, this point of intersection in statement 13, this thing that we called point, actually has to be E. That is, this betweenness relationship is true. Now we have to illustrate this. So let's illustrate that by copying that drawing and bringing it down here. So we're going to copy this drawing and bring it down and modify it. When we scroll back down, we'll find it there. So there's the drawing. Now what we need to do in this drawing is add the additional information that this point is point E. So we've proven that DEF is true. And so we're ready to wrap this up. We've proven that there exists a point F on line DE such that AFB, that's from statement 9, and DEF, that's from statement 14. That's the justification for statement 15. And so then, as we said before, the whole proof wraps up by saying, therefore the metric geometry does satisfy Peano's axiom. Well, that's the end of that proof, and that's the end of the video. Thank you.